So let's start. Uh, Today in this lab session, this is we saw multi-resolution analysis or continuous Wavelete transform. So this will cover the last section of our course. So in previous we saw short-term Fourier transform, short-time Fourier transform. So the why we need this Fourier transform. So this will we need this Fourier transform to analyze non-stationary signal, that is whose frequency response varies in time, and uh, we saw in the previous one that we have in Fourier transform we have one drawback that we have only frequency part of the signal, no time resolution will be there. And short time Fourier transform, there is only time uh, window. Okay, so in this multi-resolution analysis, so we first we saw what is multi-resolution analysis. I so um, we saw in the last section this Fourier transform is not enough to. Hello, noise coming from your side. Hello, noise is coming from your side. So, we saw in the last section that the short-term Fourier transform and this window function, all these things. So, the last section of this course, that is Wavelete transform. Okay, so just to discuss what is the meaning of this Wavelete transform and what is the need of this Wavelete transform, and most probably. Uh, all the what is the Wavelete transform and all these thing is covered in the session, right? You saw the video. So like it starts with multi-resolution analysis. Like in Fourier transform, we know that the frequency of the signal part is there. Like we have the resolution in frequency only. This is frequency and this is time section. Okay, and short time Fourier transform. There we have the time resolution, but not the frequency resolution. But when we mix these two things, we got the perfect resolution as well as in frequency and in time also. Okay, so that is the uh, portion which covers this multi-resolution analysis. Okay, so this time and frequency resolution problem is the real physical phenomena. Like in Heisenberg uncertainty principle, we know that energy and time is correlated by some factor. The multiplication should be less than. So if we have very short time, we will lose the energy part. But if we have very less resolution in time energy, then we lost the time portion. Like so, and the cycle regardless of the transform used. Okay, So it is possible to analyze any signal by using an alternative approach that is called multi-resolution analysis. Okay, so in multi-resolution analysis is employed by like so this name is multi-resolution analysis. So uh, that's what means two resolution is there. You can see as well as time. So every spectral component is not resolved equally in that STF T part that is called short time Fourier transform. So this multi-resolution analysis designed to give this good time resolution and poor frequency resolution. Like what the in multi-resolution analysis that is called MRA. So actually, what it does, actually, you saw this STFT. We have to choose some window function. So window function at every time interval, short time interval, we develop. Okay, but it did not give the most dominant result when frequency is very high. Okay, so in this one, it already covers these part in poor frequency uh, to poor frequency resolution at sorry it gives the time resolution is good when frequency is poor, okay, and the time resolution, sorry uh, see if time resolution is good and poor frequency resolution when our frequency is very high, okay, and reverse, the time resolution is bad but this frequency resolution is uh, high when we go to the lower frequency region. Okay, so uh, that's why this approach makes sense because especially when the signal at hand has high frequency component of short duration and low frequency component for long duration. So the signal that encountered in the practical application is often of this type, right? So, for example, uh, like we have one signal, like uh, this is our time resolution, and this is our frequency. Okay, so this is at zero. So this is something like this function. Okay, so if you see the this is, low frequency component is throughout the signal and relatively high frequency component for the short duration. Okay, so we need the lower frequency resolution in this region and high frequency resolution in this region. So this multi-resolution analysis is designed for this type of signal. Okay, so in this multi-resolution analysis only the term comes the continuous Wavelete transform. So the continuous Wavelete transform is developed because as an alternative approach to the short time, like we have short time Fourier transform approach first. Okay, so this is the alternate of this STFT, this continuous Fourier transform. So the technical analysis is done in similar way to this SPF analysis works. Okay. So this means that the signal is multiplied to a function similarly to the window function in the SPFT. The transform is computed separately for different segments of the time domain signal. However, there are two main differences between SPFT and this CWT. Wavelete transform is the Fourier transform of the windowed signal are not taken, and therefore this signal peak will be seen corresponding to sinusoid, that is negative frequency, are not computed. Okay, so the first thing is that, and second is the width of this window is changed as the transform is computed for every single spectral component. So which is probably the most significant characteristic of the wavelength transform, because as we vary the time, so it varies the window size which we take the in STFP signal. So So this continuous Dirichlet transform is defined as CWT at psi tau comma s is equal to psi x and psi tau comma s. This is the function. So it is 1 upon s integration xt and psi star tau t minus tau upon s dt. Okay. So So here in this equation, this transfer signal is function of two variables, that is t and this tau. Sorry, s, function of s and t. Okay, this one. So and this scale parameters, uh, the, this psi t is the transforming function, and this is also called the mother wavelet. Okay, so this mother wavelet comes gets because uh, two important properties have the wavelet analysis. Like first one is this term wavelet means a small wave. Okay, this wavelet means a small wave. So the smallness refers to the condition that this window function is of finite length. Okay, because this like we have any signal. So this window function should be at a finite length. Okay, so uh, we only consider the only small signal in a small region. So a wave refers to the condition that this function is oscillatory. Okay, this name wave because this function is oscillatory. And this term mother implies that the function with different region of support that are used in the transformation process, which is derived from one main function or the mother wavelet. So that window function can be derived with this mother wavelet, because in initial I said that as the frequency goes higher, this window function changes in automatically in this multi resolution analysis. So um, while the term translation is used in the same sense as it was used in the STFP, it is related to the location of window. Okay, because this window is changing, so that is called translation to the window from one set to another set. So, it- and also it is related to this location of this window as the window is shifted through the signal. So this term obviously correspond to time information in the transform domain, but we do not have a frequency parameter as we had before of the SPFT instead. We have a scale parameter which is defined as fraction, uh, which is defined as one of frequency. Okay, so this term frequency is reversed of the STFT analysis. Okay, so this scale is described in like so we need a scale to define this window. So this parameter scale in wavelet analysis is similar to the scale used in the map. Like in map you use some scale, no? The, 15 meters to 1 centimeter or something like that. So same thing is here. This scale parameter in this wavelet analysis. So in the case of map, high scale correspond to a non-detailed global view. So and low scale correspond to the detailed view, right? So similarly, in the term of frequency, low frequency that is high scale correspond to a global information of a signal that usually span in the entire signal, whereas this high frequency that is low scale, right, correspond to the detailed information of the hidden pattern in the signal that usually lasts a relatively short time. So cosine signal correspond to the various scales like we consider. So if we consider scale like this signal, so this correspond to like f equal to 5 and t is equal to 0.2 and sorry s in and some another signal if we need, this will be with greater frequency when f is equal to 10 and s is equal to 0.1. And if we take one s is equal to 1 and f equal to 1, so this signal will be like that. So you can see at a different scale there is different resolution we get in the frequency. So practice this low scale that is high frequency. This is a low scale, right? So this do not last for the entire duration of a signal, unlike those shown in this figure. Uh, but they usually appears from time to time as short rush or spike. High scale that is low frequency usually lasts for the entire duration of the signal. So scaling is like mostly a mathematical operation. Either dilates or compresses the signal. So larger scale correspond to dilated signal and a small scale correspond to compressed signal. Right? All the signal given like in this figure they are the same cosine signal. Okay. Only they are dilated or compressed version. The same function in if we plot another one for a small signal s is equal to 0.005, then we get more complete signal here, right? So we can choose according to our need how much scale we need for the signal. Hello. Oh, sorry, voice is not clear. Okay. 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 So, like if we take some definition, uh, if we have it, um, uh, so this continuous wavelet is defined by this equation. Let's take one example of this wavelet transform. So, like we talked about this mother wavelet, uh, right? So, one is the famous mother wavelet like Mac- called Mexican hat wavelet. It is this in the course, uh, sir, mostly about this what is called that mm, uh, what is the name? Dawichi's wavelet. Right? Uh, so in Cauchy wavelets transform are defined in some way that as the like two main type of wavelets are there, Cauchy and this Haar wavelet transform. Okay, so in Cauchy it is also known as D4 wavelets because they use four uh, uh, four scaling function. Okay, so D4, D4. Cauchy is D4 wavelet transform, right? Okay, so yes, so this maximum head wavelength is something defined psi t equal to 2 upon pi to the power 1 by 4 under root 3 sigma t square upon sigma square minus 1 exponential of minus t square upon sigma square. So this complicated form is derived from the second derivative of this Gaussian function called Gaussian function that is exponential of minus t square upon 2 sigma square. Okay, so the massive constant which is multiplied to is normal. This is comes from the normal property of this mother wavelets. Okay, so this nickname this Mexican head is because the shape of the function is like upside down Mexican head. So due to the fast decay of this Gaussian function, this function drops to zero very fast. So we can expect it is time limited in certain range, say -5 to 5. So this meets the property of this mother wavelet. So the corresponding Fourier transform of this mother wavelet, so we can write psi omega is equal to minus 8 sigma 5 by 2 pi 1 by 4 upon 3 omega square exponential minus sigma square omega square by 2. So this comes from the Fourier transform of this mother function. So it is also a very complicated form, but this illustrator of these two functions. Um, One is something like this is 0 and this is minus 1, 0. Then it comes something like this one, and the second one is something like this one. So this is for sigma equal to 1. Uh, so this Gaussian exponential term in its Fourier spectrum, therefore we expect its spectrum is roughly band limited in certain range too. So note that the low frequency component is relatively small compared to at this omega is equal to 1 point plus minus 1.5. So this result is corresponding to the that in the multi-dimensional theory, the wavelength function is the function with high frequency components. Okay, so as you perform scaling of the wavelength function, the main lobe of its spectrum will shift to higher frequency region to have finer frequency resolution. So if we come here, this Fourier transform and this short time Fourier transform and this Wavelete transform. So if we notice this forward transform is in Fourier transform we write f omega that will be minus infinity to infinity f t and exponential of minus j omega t dt, right? And this STFT that is written by this f u and some function chi, then it will be minus infinity to infinity function of t omega t minus u exponentially minus j t dt, right? So this uh, and this Wavelete transform, if we say Wavelete transform, it is utilized to f as u is equal to minus infinity to infinity f of t 1 by root s psi star t minus u upon s dt, right? So if we compare all these three, so this in Fourier transform, this convert this signal in time domain to the frequency domain by integrating over the whole time axis. But however, this signal is not stationary. That is the frequency composition is a function of time. So we cannot tell when a certain frequency rises or falls, right? But in STFT, this tries to solve the problem in Fourier transform by introducing a sliding window. Say Wt minus u is some sliding window. So this window is designed to extract a small portion of the signal Ft and then take Fourier transform. So the transform coefficient has two independent parameters. Have one is the time parameter t, and indicating the instant we concern. So the other is frequency parameter which is chi. Uh, just like that in the Fourier transform. However, this the another problem arises that the very low frequency component cannot be detected on the spectrum. So it is the reason that we use the window with fixed size. Okay. So suppose the window size is 1, then if there is a signal with frequency zero point 0.1 hertz, then this extracted data in 1 second look like flat DC. Okay, because frequency is very low. But in this wavelet transform, what we see in wavelet transform overcomes this problem. The wavelet function is designed to strike a balance between the time domain, that is finite length, and the frequency domain, which is finite bandwidth. Okay, so finite length means time domain, and the frequency domain is in we take finite bandwidth. So as we dilate and translate the mother wavelet, we can see very low frequency component at large S, while very high frequency component can be located precisely at a small s. If this frequency component is very high, then we can see at small s. But when this frequency is very large, then we can see very low s. So this is the comparison between all these three transforms. Okay. So similarly, we can see the inverse transform also, and inverse transform can be also uh, comparison like that. And next thing is we consider basic. Sorry, basis, not basic. So like basis, if we say uh, for Fourier transform, uh, complex exponential function which is exponential of j omega t is used for with the different frequency. Okay, while this STFT, the truncated or windowed complex exponential function, which is wt minus u exponentially j t. This basis is used for the STFT, while in this Wavelet transform, in wavelet transform we use mother wavelets that is scaled. So this is under root s psi t minus u upon s. So these three bases used for three transform which we see in this code. And if we saw different bases for the transform, so like if we talk about this Fourier transform, so like we have this is the real part of any uh, so the real part of the basis for the Fourier transform, that is exponential of j pi t. Then basis for the different frequency, like if we say exponential of for j 4 pi t, then it will be something more. This period will increase in this part. Okay. So similarly, we can plot the STFT basis. This will looks more Gaussian type. And if we go to the for this is for semester 2 1, and basis for different frequency like exponential of t square by 2 exponential 4 this 4 pi z, then it will looks like this one. Okay, so this is a different basis plot we can plot. Like similarly, if we saw different frequency tile evolution uh, between all these three one. So as I previously have done plotted, so this will be the frequency tile evolution. This is t axis and this is frequency axis. So this is for our Fourier transform. Similarly, as TFT for STFT, this is something like equally spaced uh, tiles will be there, frequency as well as in time. But when we saw the wavelet transform, so in wavelet transform, like frequency resolution will be here, it will be less, uh, and like this is F, okay, and this time resolution will be like something this thing. So means like we have time resolution, equity time resolution at all frequency, but frequency resolution will be at higher frequency, it will be less resolution, and lower frequency it will be higher resolution, like that. Like how we will type this thing. So next we will on this one only. So this time can be explained by this quantum physics. The Heisenberg uncertainty principle states that certain pairs of physical properties like position and momentum cannot both be known to arbitrary precision, right? So the same principle holds in this signal processing. We cannot predict both time and frequency very precisely. So the product of variation in time and variation in frequency is greater than 1 by 2. Okay. Uh, in otherwise it is called H cross Y2. So if we have in time and in omega, so it will be always greater than 1 2 this product. So this much error we always have in our signal. So it can be viewed as rectangle with constant area and different transform, adjust the width and height of the rectangle. Okay. So in the Fourier transform, the time information is completely lost and frequency is divided uniformly. But in SQL, we say this add a window to take the time domain signal. Like first we can take this window, then this window, then this window. So it resolve this time axis as well as the frequency axis, right? But we cannot zoom in a particular frequency range because this box is uniformly placed everywhere. So we cannot zoom like if we know the only in this signal we tested in a small frequency. So we cannot zoom this in SQL, right? But in the wavelength parameter, wavelength transform, we introduce this parameter S, which is inversely proportional to the frequency. As we see, if one to focus on low frequency, then larger S is used, while this higher frequency, we use small s. This flexibility increases this time frequency analysis. Okay, so if we want to say some common wavelength function, so in common wavelength function, first we saw this design equation. So in the scaling equation, um, 1 by 2 phi t by 2 is equal to summation at phi n phi t minus n. So if we take this Fourier transform on one another equation, you can write 2 psi t by. So if we take the Fourier transform of these two things, so it comes like 1 by root phi 2 omega is equal to h phi omega and phi omega. Okay, so and second one it will come psi 2 omega is equal to h psi omega and phi omega. Okay, so this phi omega and this psi omega. These are the Fourier transform of this scaling and Wavelete function respectively. So h phi omega and h psi omega. These are the discrete time Fourier transform of this discrete filter. Okay, so like we can use different wavelength function to design different type of filters. Depending on the filters, this wavelength function can be changed. Okay, so this is from my side of the today. If you want to ask something, you can ask. Thank you. Uh, and sorry, it's 15 minutes, so we can talk about some application of we can talk about some application limits since this 10 minute mode. So first thing we can use this Wavelet transform for the image compression or image mostly image processing we can say. Okay, uh, like with the compression it is called code like JPEG 2000. So before the JPEG 2000 the JPEG image compression standard. It is a JPEG image standard. So JPEG is based the discrete cosine transform that is called DCT. So however this standard divides the original image into 8 by 8 blocks and do the that DCT that is discrete cosine transform and use this different quantization table for luminescence and luminance. So we have a good compression ratio and maintain the quality of the original image. So this is used as for this compression. So if the compression ratio is pretty high, the block effect is precisely so this effect originates from the artificial division of the blocks. So this is the some how it works in image processing. And like if you so you can example. So if you see this image, this is some image which is transformed on the waste of DCT, and this image is transformed from the wavelength. So if you see in the zoom view, so this image has some blurriness, and this is more clear than this thing, right? So this is the difference between this wavelength based transform and this DCT based transform. So this can be used in this layout, like another thing is like this one. So you can see like in wavelength transform, this is one image, some image. Okay, so in this section, this actually is written when this image is divided across this x-axis, and this image is then across y-axis, and this is something transformation. So uh, that's how this works. This will transform in the image processing works. And other application is age and movement detection, uh, and pattern recognition. Second application is pattern recognition. So in pattern recognition, it depends on the computing, the features of the data. So if we first condense the signal-wise wavelet transform, the computation effort can be reduced. Okay. So once this pattern is probably recognized, we can use wavelet transform to do the finer analysis. So in this we can use this as a pattern recognition, and the most important is filter design. So as the Fourier transform can distinguish the noise and the signal age, so we can design an anti-noise filter without distortion of the original signal. Okay. So and also the most important in the end is this Wavelength and Fourier transform can be used to analysis of electrodiagram. Do you know what is electrodiagram? That ECG whenever from healthcare, sometimes this ECG have to done, right? So this is called electrodiagram. So an ECG is not smooth with many sudden transitions. Okay, this ECG comes like this line somewhere and like that. So if we analyze the spectrum noise and desired signal transition, so this cannot be separated using ordinary filter. So here this wavelet transform can also remove this noise and preserve the feature of the ECG. Okay. So there are still another application which are not noted. In short, the wavelet transform is powerful tool to solve the problems beyond the scope of the Fourier transform. That's why we use this wavelet transform. Okay. So conclusively we can say that we saw a little bit Wavelete transform. What is this Wavelete means? So that's it from my side. So this course is completed or more classes remains? Hello. Okay. Okay. Then thank you. Okay. Bye. Hello. Uh, मैं multiple class इसको use इधर आते थे ना असाइनमेंट वगैरह सेम उसी पैटर्न की लाएंगे